Okay, so this is a continuation of this final discussion of activation energy. And as we looked at in the previous clip, we started to look at an energy profile diagram whereby we go from particles A and B to particles C and D, just a very generic reaction. And we have now suggested that in order for a reaction to occur, we must A, have a collision, but must also B, have an activation energy which is satisfied when that collision occurs. So it must have a minimum amount of energy. So this is for a normal reaction. So how can we use this then in order to affect, as we've done with all of the other variables we've looked at, how to vary the rate of reaction? And if we were to now look at this diagram and try to affect this diagram to affect the rate of reaction, what we're not doing is changing the number of collisions here, because we're going to keep the concentration the same, we're going to keep the pressure the same, we're going to keep arguably the temperature the same. But what we're going to try and do is affect the profile of this diagram to affect the rate of reaction. And what we can see is, and what we're now looking at is, that there is essentially this activation energy is essentially a barrier to reaction. What we have is an activation energy, a minimum amount of energy required for a successful reaction to occur. And if we don't have that amount of energy, then reactions at specified energies like these don't occur in reaction. So what can we do? What we can try and do is very theoretically simplistic, is reduce the activation energy and essentially make the hill smaller. Seems very simplistic. It's not easy to do. However, it is chemically possible to do this. And we do that by adding a catalyst. And that's what a catalyst does. Biology use them all the time. They would use enzymes, for example. But essentially what happens is a catalyst lowers the activation energy. It doesn't change the number of collisions, but what it does do is allow the collisions that do occur to not have as high an energy barrier for those collisions to be successful. So if you reduce the energy required that a collision must have, then you can increase the rate of reaction by allowing the activation energy to be lowered. So if that is then allowed, the rate will increase. What it does is it doesn't change A and B, it doesn't change C and D, so the overall reaction is the same. However, it provides an alternative pathway, which is the kind of specimen answer. It provides an alternative pathway with a lower activation energy. And if that's the case, that then allows you to increase the rate without necessarily having increased the number of collisions. Okay, so we can add a catalyst to this. Now, on a previous clip, we were also discussing temperature. And what we said was that you can increase the temperature or increase the speed of the reaction by making the particles move faster, giving them more energy, etc. This can also tie into here, because if we've also then increased the energy of, say, A and B by making them hotter, we've essentially given A and B a bit of a head start. And so we haven't necessarily reduced the activation energy. However, we've made that energy barrier a little bit easier to overcome because we've given A and B more energy. So linking back to the previous clip, if we increase the temperature of a reaction, we not only increase the speed of them, a collision occurring, but we also increase the likely energy of a collision occurring. Therefore, it's more likely to have the activation energy. So what you see is a cumulative effect. And with that, temperature increases of rate. For the other ones, in order to increase the rate by a factor of 2, so if we doubled the rate of reaction, in order to double the rate of reaction for surface area and concentrations, for example, we had to double the concentration and surface area. But for temperature, in order to double the rate of reaction, all we need to do is add 10 degrees, because we get a cumulative effect of both speed and energy.